Watch an advanced language model agent attempt a complex, multi-step tool loop, and you will often see it fail in motion. It drops the thread of the task, repeats an error, and stalls out entirely. The hardware isn't breaking, and the model weights are fine. The failure occurs in the procedural instructions, the text-based skills that dictate how the agent uses tools and applies domain logic. The standard industry fix for this is loose self-reflection. An evaluator model looks at the agent's errors and rewrites the system prompt to try again. But an unconstrained language model writing its own instructions is a hazard. It will aggressively overwrite perfectly functional rules to solve one localized, temporary error. Unbounded text revision causes catastrophic prompt forgetting. Generating text inherently lacks the structural discipline required for actual optimization. We need to know if it is possible to optimize a plain text prompt using the exact mathematical discipline of gradient descent. This optimization landscape maps our solution. By treating text edits as gradients, edit budgets as learning rates, and test splits as validation gates, we replace erratic rewriting with controlled descent. This framework transforms unconstrained text into a stable artifact, SkillOpt. This flowchart details the architecture of SkillOpt. Optimization begins with a forward pass, called the rollout batch. The frozen target model executes tasks on a training split, compiling successes, failures, and execution traces into a single unit of evidence. Updating a prompt based on a single failed trajectory leads directly to overfitting. The model simply invents an anecdotal fix for a highly specific error. Processing tasks in large rollout batches prevents this. It exposes the consistent, systemic procedural flaws that actually require intervention. This schematic moves us to the backward pass, the mini-batch reflection phase, driven by a separate optimizer model. The trajectory evidence is partitioned. Successes are grouped to preserve what works, while failures are isolated into distinct mini-batches. The optimizer model does not execute the task. Its sole function is to act as the gradient calculator for the text space. It outputs precise, structured atomic operations: add, delete, or replace. Vague LLM self-reflection is removed from the process. It is replaced by strict, computable textual vectors pointing toward a verifiable solution. The atomic edits reach the batch-level merge and face the textual edit budget. Every proposed operation is ranked by expected utility. Then, the ranked list is strictly truncated by a hard integer limit, capping allowed edits. This limit is dynamically controlled by a cosine decay schedule. As training progresses, maximum allowed edits shrink to force the consolidation of knowledge. Imposing this strict textual learning rate blocks large semantic jumps, allowing a skill document to acquire new procedures without destroying existing rules. This section of the diagram outlines the core safety mechanisms, the validation gate, and the rejected edit buffer. A proposed edit can sound logical in text while actively degrading actual execution performance. Every candidate skill is executed against a strict selection split. If the score drops or even ties, the candidate is instantly rejected. That rejected edit is then pushed into an epoch local buffer. This creates explicit negative feedback for the next pass. The closed-loop system mathematically prevents the optimizer from repeating dead-end textual directions. The bottom section of the architecture is dedicated to the epoch-wise slow update. Text environments require optimization momentum to capture long-horizon procedural regularities. The system compares the current and previous training epochs, isolating the successes that remain stable and the failures that persisted across multiple updates. This longitudinal guidance is extracted and written into a protected, fenced region of the skill document. Fast, step-level tactical edits are separated from slow, strategic knowledge. The short-term fixes cannot overwrite the long-term lessons. The output of this entire training loop is a single, deployable artifact, the bestskill.md file. Despite being trained on thousands of execution trajectories, these final files are remarkably compact. They range from just 300 to 2,000 tokens. This brevity is the result of the validation gate's brutal efficiency. Out of countless proposals, typically only 1 to 4 edits actually survive into the final document. The surviving rules enforce exact zero-shot discipline. They instruct the agent to utilize workbook structure reasoning or maintain strict search frontier management before acting. The optimization process distills massive amounts of execution noise into pure, generalized procedural logic that fits on one page. Optimizing text instead of weights creates an immediate operational advantage, absolute cross-model and cross-harness portability. You can take a skill trained inside a Codex sandbox and drop it directly into Claude Code, instantly generating a nearly 60-point score increase. The skill transfers because it does not memorize rigid, environment-specific output formats. It captures the core heuristics of the procedure itself. Engineering teams face highly complex domains that routinely break zero-shot models. They do not always have to rely on expensive model fine-tuning to adapt. By wrapping text prompts in strict optimization discipline, the skill document itself becomes a stable, powerful, and reusable adaptation layer for AI.